All right, so in this problem, what we have is we have some information about an unknown organic compound, and we're going to want to see if we can deduce the structure. So we have a molecular formula, and it's a little bit small, so let me redraw this. So we have C8H8O2, and then we also have the mass spectrum, the proton NMR, the carbon-13 NMR, and the infrared spectra. So the way that you approach these is really kind of up to you in terms of which spectrum you feel the most comfortable initially getting information from. For a lot of students, at least in my experience, the first thing that they like to look at is the IR spectrum. So we have in the infrared 1, 2, 3, 4, 5 different signals that we can look at here. And so all in the CH stretching region, we have some peaks that are just slightly greater than 3,000. So we should recognize those as some sp2 carbon hydrogen stretches. And with a molecular formula like this, C8H8, so we don't have very many hydrogens for the number of carbons that we have. So when I see that, and I have greater than 6 carbon atoms, I'm going to look to see right away if this is paired up with a signal that could be indicative of a benzene ring. And there's a signal at 1511. So it's common to see that benzene ring stretch either there or sometimes at 16. So this looks like benzene to me. Right, and of course we could confirm that, so benzene, by looking quickly to look and see if we have signals in the aromatic region of the proton NMR and in the aromatic region of the carbon NMR, and we do. So we have a pretty good idea just from that quick glance at the infrared that we have a benzene ring in this molecule, which is really good news. That means you found 6 of your carbon atoms and some number of your hydrogens. It depends on how that ring is substituted. And we can get to that later. And so continuing with the IR, let's see if we can get information about other functional groups. So we see these peaks. I'm going to use a different color so it's a little bit clearer. So these signals here, it says 2964 to 2841. So that's the region where we typically see sp3 hybridized carbons, carbon hydrogen stretches, I should be specific. So that means there's at least some alkane portion to this molecule. There's a carbon in there that's sp3 hybridized that has some hydrogens on it, at least one. And then we have another type of carbon hydrogen signal here. So we've got this pair of signals at 2800 and 2736. So that's these two. That's really, really indicative of an aldehyde. So that is the CH of an aldehyde. And so if we have an aldehyde, right, if we're seeing that CHs, so that's what these signals are, we expect that we should also have a carbonyl. And we've got this signal at 1702, and that should correspond to the carbonyl. So what we know so far, so we're going to start kind of keeping track of our little pieces of the molecule. We know we have a benzene ring, and we also know that we have an aldehyde. And so this might not sound like a lot, but it's actually an awful lot of information if you consider the molecular formula. So with the benzene ring and that aldehyde carbon, you have found 7 out of 8 of your carbon atoms, right? You found 1 of your 2 oxygens, and we can start thinking about what that other oxygen might be actually, right? So it's not an ester if it's an aldehyde, because that would be the first thing I might think of if I see O2 and I see a carbonyl, so that's not an ester. So what else contains an alcohol? Maybe an oxygen, so maybe an alcohol. And I would expect to see an alcohol peak here. So remember, infrared spectroscopy can also tell you about what you do not have. So I would also notice from this IR spectrum that there is no OH. So I don't have an alcohol. So I've got to think about what other sort of functional groups could have that. And I don't want to give it away just yet. So we'll just kind of tuck that in the back of our minds and think about it. So now that we've got these 2 functional groups, maybe we can go to the proton NMR spectrum and see where our hydrogens are and then kind of see where our carbons are as well. So we see this 1 hydrogen singlet So in case we can't read that because it is kind of small, so that one hydrogen singlet, and it looks like it's at approximately 9.8 ppm. That's your aldehyde, right? So this is good because remember that all of these spectra correspond to the same molecule. So if we see evidence of an aldehyde in the infrared, we should also see evidence of the aldehyde in the proton. And for that matter, we should also see it in the carbon, and here we see it. 191, that looks like the aldehyde carbonyl, right? Because all of this information corresponds to the same molecule. Okay, and so kind of with that, on that same lines, we already know we have an aldehyde. We also already know we have a benzene ring. So a key piece of information that we can get from the proton NMR spectrum is how that benzene ring is substituted. So this says 2 times 2H doublet. So what it means is that this singlet is a 2 hydrogen, or this signal is a 2 hydrogen doublet. And this signal is also a 2 hydrogen doublet. So that means that we have, from these two signals, a total of 4 aromatic hydrogens. And so this gives us information about how our benzene ring is substituted. If it was an unsubstituted benzene, every single one of these carbons would have a hydrogen, so there would be 6. So we can say 6 is an unsubstituted benzene. How many hydrogens? Subtract from that 4 and you see 2. This tells us that we have a di-substituted benzene. Okay, so we know that we have 2, so 6 being the number of hydrogens on a normal unsubstituted benzene ring. Subtract 4, that tells you how many substitutions you've made on the ring. If you only have 4 aromatic hydrogens, you replace them with 2 other things. Okay. So the way that your benzene can be substituted, di-substituted, is you basically have a few different patterns, right? So your substituents, we'll just call them X and Y, could be next to each other. It could be 1-2 substitution. I could move the Y down 1 more. And that would be 1-3 substitution. And I could move it down 1 more so that these were opposite each other. And it would be 1-4 substitution. So these different patterns are going to show, different symmetries in terms of the number of signals that you would expect to see. So that's something to look at, like the number of different hydrogen signals you would expect to see. If X and Y are very different for this 1-2 substituted, then all 4 of these hydrogen atoms might even show up as unique signals because there would not be a plane of symmetry. Likewise here, we would not have a plane of symmetry if X and Y are different things. So you might see 4 different signals. Now, even in this 1-4 substituted, even if X and Y are different things, you still have a plane of symmetry vertically through the molecule that would make this hydrogen, make it a hydrogen, and the hydrogen on the other side of the X would be the same as each other. And this hydrogen and the one on the other side of the Y would be the same as each other. So we'd only see 2 aromatic signals. That's what we see. 2 hydrogens, so that's our integration. And then the splitting also makes sense. They're each doublets because this orange hydrogen is going to see the green one that's adjacent. So 1 adjacent hydrogen, so N is equal to 1, and 1 plus 1 is 2. So that's why we're seeing doublets. So this sort of pattern in particular is very characteristic of a 1-4 substituted benzene ring. So I'm going to go ahead and say now that these groups, whatever they are on opposite sides of the ring. And so we might also notice at this point, right, that if you want to do some quick math, you can see that these 2 pieces are accounting for everything from that molecular formula except for 1 of the oxygens, 1 of the carbons, and 3 hydrogens, right? Because we have 1, 2, 3, 4 aromatic hydrogens and 1 on the aldehyde for 5. And so let's look to the next signal in this proton NMR. So this is a 3-hydrogen singlet. 3 hydrogens, that's probably a methyl group. So we found our other carbon and our 3 hydrogens that we were missing from that molecular formula. The only other thing we're missing is an oxygen. So my first thought here is that maybe the oxygen is attached to this carbon. And so what I would do is I would look at the chemical shift. And we can see that this chemical shift, that number there is 4. So this looks like a carbon that's attached to an oxygen. So hydrogens that are attached to an oxygen. And so that would be an ether, right? Well, that makes sense. We were missing an oxygen. And we knew we didn't have an ester because we have an aldehyde. We definitely don't have an alcohol or a carboxylic acid because we have no OH. So that really didn't leave us many options for oxygen-containing functional groups. So we've got this OCH3. So the only thing left to do is to attach them to the ring. So we can put the ether on one side, and we can put the aldehyde on the other side. So now we have a proposed structure. And so far we've really looked at the IR spectrum and the proton NMR. So we know that our structure is consistent with these two. There's a pretty good chance that it's right, but you should always verify with all of your types of spectroscopy to make sure you can make sense of it all. So we see here, if we go to the carbon 13, so this is the next thing I'm going to go to, we see 1 signal for the aldehyde, okay. We see 4 aromatic carbons. And that is because we've got some symmetry in our benzene ring. So we have this carbon. The 2 carbons that are next door to that would be the same. These 2 carbons would be the same. And then finally this 1. So that makes sense. Okay, so we're kind of checking off our little pieces of evidence here. And then finally at 56 ppm, that's pretty indicative of an sp3 hybridized carbon that is attached to an oxygen. So that would be this carbon of your methyl ether. So far, IR, our proton NMR, and our carbon 13 are all telling us the same thing. The mass spec, we should at least be able to explain the base peak. So this is your base peak. And we know that it's the base peak because it's in 100% abundance. And if we take a look at this, it's just the loss of 1. So that's just losing the aldehyde hydrogen. So this is the loss of the aldehyde hydrogen. And that's not unusual. It's going to give you a resonance stabilized aselenium. So we could actually draw that species that corresponds to the base peak, and we probably should for completeness here. Right? So if you've lost the hydrogen, you have a positive charge here, right? So you could draw the resonance. So this is what's corresponding to the charged species that is giving rise to that base peak. So all of it is consistent. We've checked it all out. We can be pretty confident in saying that this is a good proposed structure that fits the data we were given.